Start. ठीक है? Okay, so good evening everyone. Today our group number 19 will present on the topic pH measurement and its significance in healthcare. So this presentation was made under the guidance of our sir Dr. GL Karthik. Now moving forward, these are our group members: Avni, Mrinali, myself Chinmay, Isha and Aryan. Now I'll hand it over to Mrinali.
So in this presentation, we will be talking about introduction, application, device used, video tutorial, and then future scopes and conclusion. Please change the slide. Okay, so let's see what is pH. pH is a measure of the acidic or alkalinity of a solution. It represents the concentration of hydrogen ion in a solution where lower value indicates high acidity and higher value indicates the greater alkalinity. pH monitor is essential in the field like chemistry, biology, medicine, environmental science to ensure that the solution environment maintains the necessary condition for the specific reaction or biological process. Let's see the factors that influence pH. First is temperature. When temperature changes, it can alter ion concentration and affect pH levels. Concentration of acids and bases. Adding acid or base substance directly impact pH. Basic. Next is CO2 level. Carbon dioxide can dissolve in water to form carbonic acids, lowering pH. Dilution. Adding water to a solution typically moves the pH closer to the neutral, but depends on solution's initial pH. Biological activity in living organism, cellular respiration, other metabolic activities can produce acid affecting pH of the bodily fluids. Next slide, please. Okay, from let's see the measurement of pH. From 0 to 6.9, it's acidic range. 7 is a neutral, and from 7.1 to 14, it's basic range. Let's see the analysis. From 0 to 2, strong acid, for example, hydraulic acid. From 3 to 6, it's, it's a weak acid, for example, vinegar, orange juice. 7 is a neutral, for example, water. 8 to 10 is a weak base, for example, baking soda solution. From 11 to 14, it's a strong base, for example, bleach. Next is color representation. Acid contains red, orange, yellow, depending on the acidity level. Neutral, green for neutral, green represents green represents neutral. For basic, 8 to 14, blue purple shade with strong bases typically appearing as a dark blue or purple. Next slide.
So now, as Mrinali presented, we can see that pH measurement is more than a number. It's a vital indicator of health, and real-time pH monitoring allows us to detect imbalances early, enabling personalized and proactive care. So for applications, we have mentioned three major parts that involve major pH implications. The first is blood pH in critical care. Blood pH, tightly regulated between 7.35 and 7.45, is crucial for psychological stability and physiological stability. Even minor deviations can disrupt cell function and metabolism. Some of these disorders include first, respiratory disorders. In COPD, which is chronic obstructive pulmonary disease, buildup causes respiratory acidosis. Regular pH monitoring helps adjust ventilation and stabilize patients. Second is metabolic disorders, which is the most important one. Diabetes can lead to metabolic acidosis due to acidic ketone buildup, a life-threatening condition. Blood pH tests aid in early detection and management. The last, ICU and emergency care. In critical settings, low blood pH often signals oxygen deprivation or respiratory failure requiring immediate intervention. It also helps us take care of emergency cases like accidents and etc. So that means by integrating pH monitoring into care, we ensure timely decisions that save lives and improve outcomes, making it a cornerstone of modern medicine. Next slide, please. So for the next part, the role of pH in human skin biology. The importance of pH in human skin biology is it plays a crucial role in maintaining its health and function. The skin's natural pH is slightly acidic, ranging between 4.7 and 5.5. There's acidity from acidic mantle, a protective barrier that defends against pathogens like bacteria and fungi while preserving the integrity of skin barrier, proving that without this acidic mantle, our skin will be prone to diseases. When the skin's pH is balanced, it prevents dryness, cracking, and environmental damage, keeping the skin supple and healthy. However, disruptions in pH can lead to these skin conditions, which I have written below. The first is eczema and dermatitis. Higher skin pH and eczema weakens the barrier, exacerbating symptoms, and restoring acidity helps manage these conditions, which is why we use ointments and other dermal applications, medicines. And the second is acne. Bacteria like Propionibacterium acnes thrives in alkaline environment. So maintaining an acidic pH curbs this bacterial growth and reducing the breakouts. Next slide, please. The final is the most important one, is the gastric pH in human health. Gastric pH ranging from 1.5 to 3.5 is vital for digestion and protection. The highly acidic environment activates key digestive enzymes and defends against harmful pathogens, ensuring proper nutrient absorption. However, imbalances in gastric pH can lead to these health issues. The first is acid reflux and GERD. High gastric pH, which means less acidic, often indicates GERD, gastroesophageal reflux disease, where stomach acid flows back into the esophagus, causing discomfort. Monitoring and managing pH levels with diet or medication can help alleviate this problem. Second is the digestive enzyme activation. Acidic pH activates enzyme like pepsin, which is crucial for protein digestion. If pH is imbalanced, digestion suffers, leading to a nutrient deficiencies. The third is medication impact. Antacids and proton pump inhibitors alter gastric pH to reduce acidity, but the long-term use may hinder nutrient absorption, and this is why regular monitoring helps prevent these complications. And the last and most important, stomach ulcers, which leads to many critical cases. It happens due to excessively low pH, and these low pH can cause ulcers, which is worsened by H. pylori infection or NSAIDs. Balancing these pH aids in healing or reducing the exposure of stomach ulcers. Understanding and maintaining gastric pH is essential for digestion, nutrient absorption, overall gastrointestinal health. These are the applications of pH measurements in human body.
Before talking about devices used in pH measurement, we would like to play a video explaining potentiometric pH measurement.
Many liquids are essential in our daily life. They may include water, beverages, dairy products, chemicals, acids and bases, or pharmaceutical products. The quality of these liquids is determined by their chemical properties. To assess these properties, various principles of measurement are used. One of these principles is pH measurement according to the potentiometric principle. The principle can be traced back to 1909, when the Danish chemist Søren Sørensen introduced the so-called hydrogen ion exponent pH+, to describe the concentration of hydrogen ions in a solution. This was the basis for the development of the conventional pH scale. In 1889, Walter Nernst formulated the Nernst equation that for the first time related electrical voltage to ion concentration. The Nernst equation derived for pH is the physical basis for pH measurement according to the potentiometric principle. Potentiometric pH measurement is the measurement of a potential difference using so-called glass electrodes or non-glass electrodes. In the case of glass electrodes, the pH-sensitive element is a glass bulb that is fused to the end of a glass tube. The electrode is filled with a neutral potassium chloride solution buffered at pH 7 and contains a silver chloride wire that forms the electrical connection. The reference system is located in the outer glass tube and also consists of a silver chloride wire in a potassium chloride solution. A so-called junction protects the reference system from the medium to be measured without disconnecting the electrical connection between them. The pH value is calculated from the potential difference between the reference system and the measuring system. Let's take a closer look at the pH-sensitive glass bulb to understand how this potential difference is formed. Diluted hydrochloric acid, for example, contains large negatively charged chloride ions and small positively charged hydrogen ions. When the pH sensor is immersed into this acid, the hydrogen ions are able to penetrate the boundary area of the glass membrane, the so-called gel layer. The considerably larger chloride ions remain in the solution. The result is a charge separation. The same process occurs on the inside of the sensor with the neutral solution buffered at pH 7 that has a constant concentration of hydrogen ions. If the hydrogen ion concentration, hence the pH value on the inside, differs from the concentration on the outside, a measurable potential difference forms. If the hydrogen ion concentration on the inside is lower than on the outside, as shown here, the measured solution is acidic with a pH value lower than 7. If the hydrogen ion concentration is identical on both sides, no potential difference forms and the measured solution is neutral with the pH value 7. The measured solution is basic if the hydrogen ion concentration inside the glass bulb is higher than in the measured solution. pH measurement with non-glass sensors is based on so-called ion-selective field effect transistors, short ISFET. They use a MOS transistor arrangement, which contains a pH-sensitive layer instead of a metal gate. Positive hydrogen ions forming at this layer cause the charge to be separated on the other side. As a result, the area between source and drain becomes conductive. The resulting flow of current is in direct proportion to the pH value of the medium. Just like the glass sensors, the ISFET sensor also needs a stable reference potential. The potential that forms at the ISFET can then accurately be measured against it. The reference system is also protected from the measured solution by a so-called junction. The potentiometric measuring principle by Anderson-Hauser enables highly accurate pH measurement for better product yields and less waste. We offer a solution for all applications, even in those industries that do not tolerate glass. For further information on liquid
Now that we have understood how pH is measured, we can have a look at the devices used for measurement. First is glass electrode. The potential of the glass electrode is written by means of Nernst equation given here, where E naught is the standard potential, R is the gas constant, T is absolute temperature, and delta pH is deviation in pH from 7, and F is Faraday's constant. This relation shows that the EMF developed in the electrochemical cell is the linear function of delta pH. For for making pH measurement, we have a setup of a glass electrode and a reference electrode, often calomel electrode, are immersed in the liquid in the solution, and the voltage difference between the electrodes is amplified and displayed as a pH value. The pH meters often include calibration and temperature compensation feature. Microcapillary glass electrode are preferred when it is required to monitor pH continuously. For example, during surgery, it is useful when a very small volume of sample is to be analyzed. Glass electrodes also have a limitation. Prolonged exposure to blood can damage the glass electrodes, affecting its performance. Protein deposition can cause a decrease in the electrode's sensitivity. So, to minimize this effect, electrode should be cleaned regularly with pepsin and zero point 0.1 normal HCl and wiped with tissue paper. Please change the slide. Second device is pH meter, most commonly used device for measuring pH in urine analysis. These meters typically consist a probe electrode that is immersed in urine sample. The probe measures the hydrogen ion concentration, which is directly related to pH value. There are several types of pH meters used in urine analysis, including a portable pH meter. These are small handheld devices that are easy to use and ideal for point of care testing. Second is benchtop pH meters. These are larger and more accurate and often used in laboratories and clinical testing. Uh, Third is pH strips. They are paper strips coated with pH indicator that changes color depending on the pH of the urine. While not as accurate as pH meters, they are convenient for quick qualitative assessments. Next slide, please. Third is gastric pH monitoring devices. They typically use pH electrodes to measure the acidity of stomach contents. These electrodes are often small flexible tubes that are inserted through the nose into the stomach. There are two main types of gastric pH monitoring devices. First is intra-abdominal pH monitoring. This involves inserting a pH electrode directly into the stomach. The electrode can be left in the place for several hours or days to record pH changes over time. And second is wireless pH monitoring. This uses a small wireless capsule that is swallowed. The capsule measures the pH and transmits the data to a receiver worn by the patient. Both types of devices provide valuable information about gastric acid secretion and can be used to diagnose and monitor conditions like gastroesophageal reflux disease and peptic ulcers. The next part will be explained by Chinmay.
So now moving forward, there are several devices used for pH measurement in wound care, where uh, some of it, some of them have advantages and many applications, including pH meters, which is traditionally used where a portable pH meter with electrode is directly placed on the wound surface. It provides precise pH measurements and is suitable for wounds of varying sizes. Next comes pH strips. They are quick and easy to use, which are dripped or placed in contact with the surface of the wound for pH assessments. So the change in color indicates a visual indication that the pH level has changed. Although they are quick and easy to use, but they are less accurate compared to pH meters. Uh, Third come pH sensors. It can be used via the wireless technology and is integrated into dressings or bandages for continuous monitoring. So they provide real-time data of the pH readings. So they are ideal for use in chronic wounds where long-term monitoring of wound healing is required. Lastly comes pH test kits. So these are the combination of the above devices and include pH meters, strips, or sensors along with buffers and cleaning solutions. So for comprehensive testing, it offers a wide range of options for different wound cares. These are things will be explained in the next class. And now moving forward, I would like Isha to conclude with scope and conclusion.
Now I'll be talking about the future scope. So, future scope in healthcare includes the tools which are invasive, portable, and precise also. The advancement in real time monitoring devices will help in getting faster and accurate results. Personalized medicines has several benefits which allow us to continuously monitor the body conditions. Using of technology is more effective for personalized healthcare. Next slide, please. Now, concluding this, measuring pH is very important, understanding how our bodies are working. As technology gets better, we can use pH measurements in many more ways in healthcare. Early detection. This includes early detection, finding health problems sooner, accurate monitoring, keeping a close eye on how a patient is doing, personalized treatment like tailoring treatments to each individual patient, and by using better tools to measure pH, we can better manage diseases and improve people's overall health. Thank you so much.